people there that I definitely know. I can expect some heckling later on. That's right, so Barking Riverside. Thanks for the introduction, Colin. Picture there is the first test train that ran on the Viaduct at 8 o'clock in the evening back in last May. So I actually got to ride on the first train on the Viaduct, which is a bit nerdy, but I really enjoyed it. Anyway, let's crack on. Interesting project, Barking Riverside. So there's a local vision within the Barking area where they wanted to develop some brownfield sites. Barking Riverside is where there used to be 3 power stations on the banks of the Thames. And that's where the Riverside development is located. And there's plans there for 10,800 homes. There's other developments in the area, in the Bean Park area, which people might have heard things about the new Bean Park station and yeah, the political chaos that's ensued on that one. And there's another scheme that we'll touch on later on, which is Castle Green. That's what the Barking Riverside development looks like. In red there is the principal part of the extension from the national network at the top of the screen down towards the banks of the Thames. So as we've already said, it's 10,800 homes with another 65,000 square metres of commercial, retail and community facilities. But the development cannot happen sustainably without the provision of appropriate transport infrastructure. Lots of schemes have been looked at, extending Docklands Light Railway, putting an enhanced bus network in, even tram systems are looked at one time. But the one thing that actually was affordable and could be done was the extension of the national network as part of the overground concession into Barking Riverside. Project was valued at £327 million. That's all in, all the way through from commencement of design to completion. The project is currently on budget. We're going through closing out the contract at the moment. So overall, it's 4.5 kilometres of track that extends from the existing Gospel Oak Barking line at Barking Tilbury East Junction and the extension delivered overground services to a new station at the heart of the community. Construction began in autumn 2018, although we did actually start earlier, resectioning the overhead line so we could get efficient isolations. And then train services commenced last year in May of 2020. It's whole car service, 15-minute interval. Lots of stakeholders involved in negotiating the projects and that. So I was appointed as DPE when we actually started single option selection, the end of feasibility. And then I was the DPE through the Transport and Works Act process to get and then the detailed outline and detailed design all the way through. So we had to deal with Network Rail, Strategic Freight Network, Barking Riverside Limited, London Borough Barking and Dagenham, DB Cargo, lovely people, Legal and General, High Speed 1, and you'll see why in a minute, Lineside Neighbours, New Schools and all the tox and fox that were affected. We took a unique approach to this. We went for a build-only contract. So Rail for London Overground provided a Grip 5 design. We also required the designers to produce a design that was fit for purpose instead of the norm that's in the industry, which is reasonable skill and care. Fit for purpose has a higher level of integrity to the design, such that you can potentially, I know people don't like the word warranted being used, but you can warrant the design. That being said, the Grip 6 to 8 contractor had some design still to do. There's no point us detailing secondary steelwork, detailed rebar and proprietary systems, because that's where they can leverage an advantage. We don't do temporary works. Lots of other things you can't actually design, like SSI data that comes during your Grip 6 process. We couldn't stage the OLE and stage the signalling, so that's putting too many constraints on the delivery group. We also had to collaborate quite closely with Network Rail's TENI group and the comms field services teams on aspects of the fixed telecom network, FTNX and GSMR works, because we had to extend GSMR, which, yeah, that caused a few problems because all of the technology we were able to specify was suddenly obsolete and we couldn't get ourselves on the trial certificate for the trial technology, but whatever. So the scope of works, really the project split itself into a couple of main areas. So one was what we called on network. So that was existing infrastructure to the east of Barking Station. Luckily for us, it was a 4-track formation with only 3 tracks in it. And there was an old down goods line that was abandoned back in the late 70s, early 80s. So we were able to take that track bed as the footprint for our new up Riverside. So that entailed 3 kilometres of new ballasted track, 13 renewed 4-track OLE portals, 8 new 5-track or more OLE portals. I think most we spanned was about 55 metres with a single portal. 62 new overhead line structures, new OLE neutral sections, 102 OLE pile foundations, and then the various S&Cs to get us off of the Tilbury lines onto the Riversides and back on again. To make everything fit, we had to thread through the eye of the needle, which was the Alfred's Way Bridge at the London end of the site. That meant we had to stretch out the Ribble Lane sidings that were currently there so that we could free the footprint up to realign a couple of goods lines and squeeze the new up Riverside in. So there's a short section of bidirectional track where the down goods and the up Riverside actually run into each other. There was a kilometre of track in there as well where the formation was so bad that we had to do some fairly significant formation remediation and of course signalling works. Once we're off of the existing network, we're onto the viaducts. So there's a north viaduct and a south viaduct. The north viaduct is a 300-metre long approach span, which is founded on a ground slab. This is where things start to get impressive in terms of piling. That's supported on 244 50mm diameter, 12-metre deep piles. There was a short retained fill ramp leading to a E-type steel underbridge, then 11 40-metre long steel composite bridge spans, an E-type steel underbridge at Choates Road, and then following on from that down to Barking Riverside Station, 43 number 25-metre long concrete viaduct spans. That's all supported on 560 1.25-metre diameter piles, the 30 to 40 metres deep. There was a box over the up Tilbury that required some 1.4-metre piles, 20 of the buggers. They went down to get, again, about 40 metres. And then one bit we'll cover in a little bit of detail later on, there was 9 1.5-metre diameter piles to 40 metres deep, which we had to bore between the high-speed running tunnels, with them still actually running their trains at full line speed. On the viaducts, 1.5 kilometres of twin-track slab track, 52 number twin-track OLE portals, and 3 kilometres of new Series 2 overhead line equipment. And all that would give us is 4 trains an hour Barking Riverside to Gospel Oak. It would also enable us to meet C2C's future service requirements. We did that by making sure the traction power supply improvements in the area were fit with the future aspirations of C2C to introduce Class 720s. At the time, we were also looking to utilise the possessions so that Network Rail could build Bean Park Station. That's fallen by the wayside. And another output of the project was that all of the existing Ribble Lane freight sidings were to be cleared for GB2 gauge, because prior to us undertaking works, only one siding was free, and that had a constraint for freight from Europe coming into high-speed one exchange sidings. And we also made sure that the system was robust for 2 trains an hour electrically hauled in the peaks, because at the moment a lot of the freight on the Tilburys is actually diesel hauled. So in a nutshell there, really, that's the on-network alterations that we had taken out of the Form B. At the top you've got what the railway looked like before we started. At the bottom in red is all the new infrastructure that we added. And you can see where we've moved things around, where the viaduct is and runs over and then down to the Thames. The design philosophy, basically I'm lazy, so we decided to keep it simple, stupid, because I can deal with that as a DPE. We decided to modularise everything as much as possible. So we decided early on to standardise the piles for the overhead line system. So everything would be founded on 610mm LME tubular piles. We actually found out we could actually adopt a standard embedment depth as well. So do it once and repeat it many times. It brings big benefits to you as a project. And if we got to things like between 2 or 610 LME tubular piles in a row and cantilever off of those, makes things so much simpler. We adopted Network Rail standard design E and U decks for the bridge structures. Although one of the U decks we did actually max that out to 40 metres. And yeah, that was a bit of a challenge for lifting it in. with the UK to actually drop that in all in one piece over a 2-day period. We also adopted standard precast beams for the concrete viaducts, so that everything could be made in one factory, all the same size. Very, very little difference in the lengths, but everything. And we had modular viaduct parapet units and standard blisters for the overhead line structures, which could also be used for location cases, track equipment housing, base locations, for rail lubricators. You name it, any of your line side infrastructure would fit on a standard modularized thing that we literally just hang on the side of the viaduct and concrete in place. So some of the pile depths I referred to were quite deep, I think you'll agree. So some of the geotechnical issues we had was the ground had some very variable ground conditions. Alluvial deposits, peat to 5 meters depth in places, a very high water table up to 1 meter below ground level. The minimum for quite a bit of the site that we could actually get decent bearing pressures at the end of the pile was 29 meters, although other areas it was a lot deeper. We decided to oversize the piles due to the ineffective upper length and the shear forces that they'd see in some of those areas. So when you look at the geotechnical sort of profile map there, you'll see that things are all over the place. You haven't got a consistent geology down there at all. And we did actually find some slip faults in the geology down there as well. Where we found that we had problems and we thought there was going to be some serious issues with the slip planes and faults, we did geophysics as well, so that we could take your traditional borehole data, as you've got here on the right, and overlay that on the geophysics to see whether the borehole data correlated in that location, and then see what the geophys was telling you on the left as to what you were likely to encounter elsewhere. Formation and trackbed, this is on network. We were compliant to TRK 4239, but because the ground was so poor in so many areas, we used GSLs in some areas and deep capping layers, and we optimized those. As it turns out, we were able to use steel sleepers for the sidings as a new build. One of the advantages on soft formations of steels is they've got less dead load. That's worked well on the fens. In the end, we actually ended up putting all of the new up Riverside from Alfred's Way to virtually Barking Station on steel sleepers, which massively improved productivity. One of the reasons we did that was we were just getting into the real thrust of delivery, and COVID hit and lockdowns hit and possessions were lost. And we couldn't afford to put another 1.5 to 2 years on the programme. So we had to go back and look at our material choices and what could we do. So steel sleepers. There's one FBS turnout off the Down Tilbury onto the new Down Riverside. Again, there the ground was exceptionally soft, so we used micropiling on that, and we also micropiled the ballast slab transition areas as well. So they were micropiled, then we had GSL on top of that, then geogrid, then ballast to stiffen up the formation. And I have to say, at the ballast track interface, it's not been touched since it went in. It's been running for almost a year now, and we've seen absolutely no loss of track geometry there at all. So that actually worked quite well. Gauging, alluded to that earlier. I see Steve Valentine's on here, so he'll probably tell me off about this later on. Gauging was as per normal. We used Clear Route 2. In Ripple Lane siding 1 was only GB2 gauge. So we had to clear the others to GB2 gauge, which is really just the ground signals at the country end. The problem with GB2 gauge is you can run it in clear route, but we did actually do defined gauging as required by the BSCN because a lot of the vehicles are in the clear route library, the Continental vehicles. So we did define gauging to make sure that the Continental wagons that are going to run in there would be okay. One other thing we did find was we did need some blockades. So to build a box over the up Tilbury line to put the viaduct on top of it, which we'll come to later, we had to have a diversionary route for freight services. And we found that the diversionary route that went through Upminster for the vast majority of freight was actually foul. So the vast majority of freight gauges, even though it's shown as clear in the sectional appendix, and we had to undertake some works there to clear Upminster platform as early works for the project to enable the diversionary route. A very quick typical cross section through the sidings. There you can see one of the big multi-track overhead line ports we put in. We've got the Down Tilbury, the new up Riverside, and we've got 3 sidings there, which are the GB2 reference gauge, and then we've got the up Tilbury there. This is towards the west end of the yard. There is actually another siding that sits between the up Riverside and the Down Goods. Yeah, which is a head shunt to store crippled wagons on. Challenges. First challenge we found, the high-speed one running tunnels. So we've got a nice curved viaduct that we're turning through a right angle off of the Tilburys to go down to Barking Riverside Station. And right in the middle of the site were the high-speed one running tunnels. The one problem we had was that if we were to put piles where we needed them for all of the piers to make everything work, we couldn't do it because the high-speed one running tunnels are in the way underneath. So we had to come up with a design and form of support for the steel span there for the piling that would enable us to support the viaduct. So there you can see the piles actually run between the 2 high-speed one running tunnels. You've only got about 2.7 metres from the edge of one of those piles to the outside edge of each one of the tunnels. That took a lot of negotiation with the high-speed one. We ended up, let's see Jim Bushell's on here, we ended up working with Sensieve to install a meshed network system inside the tunnel that would report on tunnel movements. And that worked well, apart from high-speed one insisting on some rather tight tolerances for the thing to alert, which meant that every time a train went past, it started alerting. But we did discover some interesting things about the way those tunnels were actually moving and working, which we shared with high-speed one since. The other thing you can see here is this little box. I don't know if you can see my cursor to the right here. It goes at the decks, but it went straight through the up Tilbury. So we built the world's smallest tunnel over the up Tilbury and plonked the viaduct on top of it. And we built that in a 6-week blockade to do all of the piling that was required for it, build the pile caps, and then get everything out of the ground so we could start building. If we had done that in weekend possessions, it would have been something like 6 months worth of weekend possessions. And as we would have to have taken down the overhead line every weekend to get in there with the piling rigs, you could bet your bottom dollar that one weekend it was not going to go back up again or stay back up after you put it back up. Yep, so back to high-speed one quickly. So each tunnel has a 3-metre surrounding annulus, which is a no-go zone. We said how many piles we needed anyway on that. So the piling was done under liquid support bentonite. The piling was to be carried out. They would not cover speed. Prior to the project actually starting, 2 guys from my team at Overground went out and surveyed and scanned the high-speed one tunnels to locate them to an accuracy of plus or minus 20 mil in our federated bin model. The one thing we did find was the high-speed one really didn't know too much about their grid. They didn't even really know where their tunnels were. So we got University College London to create a transformation from the CTRL grid to OSGB 36, then into London Survey Grid 2007, which was the engineering grid we were using on the project. That was fun as well. The other challenge we had, so we've got a railway that basically rises up, grade separates from the existing lines, comes over high-speed one, over the Tilburys, then comes across a little bit of land outside the railway boundary, has to go over a road. Just as we're going over the road and just as we get beyond, we've got a set of 400 kVA transmission lines over the railway. So we had to maintain highways clearance under the road bridge, and we had to maintain electrical clearance from the catenary wire to the 400 kVA lines there. And it was a bit of a challenge to actually balance off the 2 sets of clearances. We ended up with about 100 millimeters of tolerance for the build vertically. The reason we used the catenary wire as the point of demarcation for electrical clearance from the ultra high voltage lines was we had to think about somebody maintaining the overhead line in the future. So you've got a man stood in a mute bucket. You take the floor of the mute bucket as being the standing surface on which he's working and use that as your dimension for clearance to the overhead line. You're never going to have the floor of the mute bucket higher than the catenary wire. So we chose that. So the requirement there was for 13.6 meters clearance from the 400 kVA line to the catenary, and we could just squeeze it. It was really threading the eye of the needle through that point there. And that's the vertical profile that we sort of ended up with for the viaduct, where grade separates and comes over. So bearing in mind the blue's your vertical and the red's your horizontal, we've got a nice little roller coaster sitting in there. Viaduct itself was really quite simple. 1.5 kilometers of concrete steel viaduct and composite bridge spans, 1.5 kilometers of twin slab track, 52 number twin track OLE portals and parking Riverside station. The viaduct construction was really quite simple. We standardized on pier arrangements and piling arrangements. The viaduct articulation was such that we were using 25-meter spans connected together at a fixed pier to make a 50-meter deck. So you're always running 3 fixed, 3 fixed, 3 fixed throughout. Some of the challenges we faced. So first off, when we come off of the Tilburys and we start moving up towards the viaduct and the approach ramp, that's a 1 in 40 gradient that crests onto a 225-meter radius curve with CWR for noise limitation. It's quite a steep gradient to get over the high-speed one exchange sidings on the other side. We're at 1 in 34 there, and the radius is rolling off at 225 up to 600 meters radius. Then we have to say under the ultra-high voltage transmission lines before rising to give permeability beneath the viaduct. We face lots of challenges from people saying, why don't you run the railway at ground level? Well, if you've got 10,800 homes being built around your new railway, and you've also got a couple of roads that are going to cross it, the last thing you want to be doing is installing brand new level crossings, if you could get a level crossing order. So we carried on running it elevated. And the other thing is, with the ground conditions out there, they were so poor anyway, we'd probably have ended up doing a piled slab at ground level to support the track anyhow. Very early on in the project, we actually wasn't just the 225-meter radius curve. We modelled the entire alignment of the viaduct. We used Vampire and Dynamics to determine the best track parameters for performance, especially T gamma. We'll come on to that in a minute. But we modelled the line speed, which is 40 mile an hour with a 10 mile an hour over and under speed, with and without check rails, with and without gauge widening, tear and crush for each vehicle. And then we took a theoretically overly torsionally stiff primary suspension to produce higher angles of attack and ran that to see what the impacts would be in terms of rail wear and system wear and forces. And University of Huddersfield did that for us. So basically, we've got a load of outputs on the modelling that we'd undertaken, and that's first off, Y over Q, not bad at all. So we didn't get anything significant in terms of wheel unloading. You can see there we've got the checked case, the unchecked case, and you can see the difference that it makes on your Y over Q values when you have or haven't got a check rail, which is quite interesting. We looked at T gamma because we wanted to understand the propensity for RCF generation or for significant wear to occur. So we looked at the contact patch energy on each one of the axles of a bogie. We did actually look at leading and trailing trucks as well. So what we did find out is that T gamma values for the high rail were found to be lower in the unchecked case. That resulted in the loads being shared between the tread and flange contacts. On the low rail, although in the unchecked case, the tread contact reacts to all of the low rail forces, and T gamma values are higher in this configuration. So basically what that means is you're potentially going to see more head wear on the low rail than you're going to see gauge corner wear on the high rail. Basically, with that check rail present, because the check rail actually makes back of flange contact, and that is taking some of the energy out of the system and putting it into the check. So the recommendations we made, the modelling, and that was for crush laden state, peak vehicle Y/Q was set to the limit value of 1. So that gave us a peak wheel lift of 0.8 millimetre relative to a limit value of 6 millimetres. And those peak values were predicted for the high rail. So we actually carried out additional simulations of the high conditions. And again, the Y/Q value only went up to 0.42 with a corresponding wheel lift of 0.88. So what we were able to conclude from that was that even though it's a 225 metre radius curve running with 100 mil of applied cant, and I forget what our cant efficiency was, but it was pretty damn high, we didn't actually need a check rail, which is good because that saves money. We also found there was absolutely no benefit to have from gauge widening, which I found surprising. All the cases studied were at a high cant efficiency greater than 80 millimetres. And there was not a significant additional benefit demonstrated in reducing the applied cant and increasing the efficiency. So we were looking at, as part of the modelling as to whether we could play around with the ratio cant to cant efficiency, and if that would make a difference to wear and to T-gamma forces. As it turns out, it didn't really. So we did end up with a maximum cant efficiency at one spot of 122.6 millimetres. So that was something I had to get signed off by professional head of track at Network Rail. So now quickly onto the Viaduct track form. We chose to use the POR slab system. It used to be called the OBB POR slab. It's now called STA, Slab Track Austria. They're basically 5.2 metre long factory made precast slabs where the geometry is actually cast into the slab. They arrive on site with everything that you need fitted to them: rail pads, angled guide plates, Voshlo clips and screws, you name it, the whole lot, apart from the rail, of course. And all you have to do is basically place the concrete that's coloured green here as part of your setting activity. So your decks and your deck intermediate slabs are already cast. All you have to do is set the slabs to line and level, install the rails, do a final level check, and I can see Jim Bushell's probably gnashing his teeth at this one, and then pour the concrete and jobs are good. And obviously it wasn't as easy as that. That's what the Viaduct looks like. That's just before we went into service. So what you can see there is on the left hand side, that's you're stood on the down Riverside line with the right with the up Riverside on the left. Those are the POR modular slabs. The little square things are the shear keys, actually keep them located in position. If you were to have a need to remove one of those slabs, you can do it quite easily by breaking out the shear keys, removing the rails and dropping a new slab in. Obviously, you need to get the right slab manufactured. We had, I think it was 800 slabs and 90 different moulds were needed for the project because of the geometry. On the right, there's a special type of slab that we used at the deck ends with what we call bridge support plates, BSP plates. And we'll come on to the reason for those in a minute. The only other thing to point out as well with the slab track there is the yellow clips are all low toe load fasteners. So they've got about 50% of the toe load of a standard fastener. We did that to avoid the need to put rail expansion joints on the viaduct structure. So we worked through the requirements of what you'd have to do for managing CWR stresses, because on the viaduct you stress 21 degrees anyway, this slab track. And we found that we're able to get away with the need for putting in bespoke rail expansion joints on the structure, because we could predict how the rail was going to behave independently of the structure, and the structure's getting hot and cold, and when the rail's getting hot and cold. So those bridge support plates, deck end rotations, reserve axial rail stress. It's a bit of a mouthful, this. If anybody's actually done any structures design, especially for slab, then the Eurocode EN 1991 defines the requirements for design of structures and traffic loads. The Eurocode is good. Whilst it addresses the basic requirements for structural performance for specific load cases, in this case load model 71, whatever that, it doesn't really address the impacts of this on the track system. So what we can actually say is that EN 13481 Part 5, Railway Applications, Track Performance Requirements of Slab Systems, doesn't mesh at all well with EN 1991. And that can lead to structural designs frequently leaving the track system specified with complex issues to resolve. And that was the case at Barking. Basically, what the code enables a structures designer to do is design something that doesn't work and then say, oh, but the track designer can sort that out later on. It's pain. So the base parameters that you've got in Eurocode one is a 25.5 ton axle load, average speed of 200 kilometers an hour, a minimum radius of 1500 meters, SEN 60 rail, load model 71 as defined by the code. And then you've got load model SW0 and what we call an alpha factor of 0 to 1.5. While we were developing the design, the SEN committee was going on quite a journey, which resulted in the publication of a paper, SEN TR 17231 in 2019, after we'd finished our design, which basically told us that we had a problem, but there was a potential solution. Now, we were aware of this, or I was aware of this, and so we already were working on the intervention that was going to be required, which was the bridge support plates. But why is this an issue? Well, first off, these are the limits in the Euro code. Well, 1500 meters is not 225 meter radius. We were using SEN 56 rail, not SEN 60. Load model 71. Yeah, okay, fine, great. 25.10 axle load, but this is passenger only railways. Only if we're going to see about 16.5 different alpha factor could be applied to the sort of railway that we're working with. So the Euro code didn't really cover off our specific case. So I'll skip over that slide. But Barking Riverside, we had a problem with deck end rotations. So basically, the injection should be 2 milliradians. On ballasted track, that's not so much of an issue because you're using concrete sleevers and ballast. So all you're going to see is rapid deterioration of the ballast, which could result in twist development of deck ends and a reduced asset life, but it's not really going to be that much of an issue. The mitigating factor becomes the fatigue stress limit of the rail fastening and the stress capacity of the rail itself, because nothing else has got any give in it, basically. So we adopted the Deutsches Bahn design for a very resilient plate and clip arrangement for the first 3 rail seats of butt in a free deck end. We call those USP plates. The capacity of the rail to solve. So what the plates enabled us to do is, rather than give you the standard stress capacity of a clip in terms of what it can take from deflection, we virtually doubled that. So it could go up to, I think it was 27 kilonewtons before you start to overstress the clip. And that worked really well. But that's only addressing the clip. It doesn't tell you what's happening with the rail. So what we had to define and work out was that you could get high local rail stresses where the bridge deck ends meet. And those rail stresses are going to be either from the bridge deck ends moving in and out, or the rail moving in and out, one deck being deflected while another deck's being lifted up, and also from your nosing forces. What that all ends up to do is basically give you a whole lot of things that you have to consider to work out what's going to happen to your rail. The reason we were concerned was at 225 meter radius, you've got quite a high level of stress in the rail anyway. The rails when they're rolled have already got a reserve strip, or a residual stress in them. So you've got some of the stress capacity of the rail already taken up just from the rolling process, the manufacturing process. You then bend the rail around a curve on site and you're putting bending forces into the rail, and then you subject it to traffic loadings and you apply even more force to it. And what you don't want the rail to do is get to its ultimate limit state where it's going to say, oh my God, I give up and break. And that's what we were concerned about here, is whether what's happening at these deck ends and the deck end interactions is such that we are either going to see a reduced stress life of the rail, or we're going to be okay. And the answer is we don't know, because we're undertaking monitoring on the deck ends to define exactly what's happening on the rail. In effect, we're in a no man's land here, because no one's got any real decent research on what's happening on axial rail stresses anywhere. So just some of the calculations that you have to go through. What we ended up with was we were looking at the rail, looking at the centre line of the rail and out to the rail foot, and then working out what was happening with the stress components within those particular areas of the rail. Those are all of the various figures we found for 0, 10, 20, 30, 40, 50, 60, 70 millimeters. Current theory says that you should be able to accommodate 112 megapascals of reserve stress in a rail. We actually went over it, so we're at 126 or 124 megapascals. That is potentially an issue, and that's why we're monitoring it in service. Now, we actually believe we're probably closer to 80 to 90 megapascals, so we're below the 112 megapascal limit. The thing is, we just don't know, so we need hard data to tell us. Perhaps I'll do a paper on that in a year's time. The S&C at Barking Riverside. Probably the quickest component approval process I've been through in my life. So again, we carried on with the Paul modular slabs, a unit design of modular slab for S&C. That's combined with a base plate from Schwehag, the DFFSW series base plates. Really quite simple. Slabs arrive on site with big holes in them. You hang you place your base plates into the pockets in the slabs, hang your rails, line and level everything. One stage out there, you get your slabs set to where they need to be within like 3 to 5 millimeters. Concrete the slabs in, then you build off of the slabs, then you grout in the plates. We took our time over this, but ideally this should have been done in a factory and the slabs delivered with the base plates already cast into them. We learned quite a few lessons on that. The other thing on the S&C is Uni-style point operating equipment. So you can see there's 2 drive units on each turnout leg. This is CV10 scissors crossover. So we've got a toe drive, we've got a heel drive, both units lock and detect, which means we've actually got enhanced detection capability on the C switch compared to what would be normal with a tubular back drive. There's no stretcher bars when you have Uni-styles, so that's great. One less thing to have to worry about. Yeah, actually quite pleased with that. Couple of detailed drawings of the Schwehag base plate system and the clip shoes. We've got 2 types of clips. We've got SKL12 in orange, actually in McLaren papaya orange, and then we've got I forget which clips those are. I'm sure Paul Lindsay will correct me later on, but they're in McLaren roving blue because those were the colours of the Formula 1 team in the year I got product approval. The reason we chose the Schwehag base plate for the S&C track form, we wanted to take a different approach to resilience. So traditionally what happens is people will design for a static stiffness, and that will normally be in the range of the normal 25 kilonewton spring rate for the system. We didn't. We designed for a deflection, and from that we defined a permissible range of stiffnesses for the base plates. So if you've got a rather large footprint base plate like you're going to get underneath a cast crossing, if you had a standard 25 kilonewton pad in there, it is potentially going to be the wrong stiffness rate for the footprint that you've got there, because stiffness relates to area as well. So we defined a permissible range for stiffness for the pads, and then modelled with Schwehag what we're going to get, and we've actually achieved 1 to 1.5 millimeters deflection across all of the S&C, including the cast manganese crossings. That's good because it means that you're not suddenly seeing a change of stiffness from one type of base plate underneath a cast crossing to another. 2 forces hitting your manganese, and it's working really well. We are getting the 1.5 millimeters, and it's also incredibly quiet, which I found quite surprising. I thought we were going to get noise effects, and we didn't. Getting to the end of the viaducts. That was looking like. Quick cross section through the station. Again, we carried on using the beams that we'd used for making the main viaduct, just changed a couple of component designs. So again, the station was modularized throughout in terms of manufacturing one compliant clearances for overhead line accordance with GL 1210. So we've got the 3.5 to life parts of the vehicle. Follow-on projects after Barking Riverside, and sort of mentioned a couple of bits and pieces previously. First one is Castle Green Station. I won't bore you too much with this because it's not going to happen in the very near future, that's for sure. But basically, the London Borough of Barking and Dagenham and the Greater London Authority have got a plan to put the A13 underground and build more housing on top of it. So Castle Green Station would go where that sort of funny red mark is there. And what's currently a major highway here will now have more housing built on top of it. Why did that matter to Barking Riverside project? Well, we designed the station. But we did a bit more than design it. Because when you go to where the station's going to be, we made sure that everything that we built in that part of the world was compatible with the station in the future. So the overhead line is set for the platform to be there, so you get the required clearances. Signals have been sited and installed, so that in the future, if a train was to stop there, the signal's in the correct position for the platforms. You've got a completely sterilised area between the two lines for a 10-metre wide island platform, so you've got no problems with construction there. You can go and do whatever you want between the two running lines. Yeah, we put the maximum amount of passive provision into things. We also developed a follow-on design for the rest of the freight lines there to create what's called Ripple Lane Nodal Yard. So that would be a new nodal freight yard capable of holding at least 4 775-metre long freights and 1 700-metre long freight. And if you take some of the other mods we've done in the area, you could probably squeeze a 5th 775-metre long freight in there. The benefit of that is that the current sidings are too short for most of the consists that run on the Tilburys. So you're not able to actually stack freights and fly across the North London line and the Gospel Oak Barking line to West Coast Main Line or other places. Also, if we can double the length of the freight trains, we double the availability and the capacity of the route. So we produced an AIP, and that's now gone over to Network Rail's capital delivery team, who are now looking at the insanity that is the S&C that I designed for the country end of the site and trying to work out how to make it happen. But I'm getting too many phone calls on that. I wish I hadn't done it. So really, that's the end of the presentation. Just want to say thanks to the guys from my team that were involved in this. Xavier is an excellent civil structures building engineer. Adam Smith is my project civil engineer. Felix Barton and Rich Winthrop, who did top over survey and geospatial engineering. And some really good guys from Network Rail who pitched in and helped immensely with the initial feasibility and option selection. Guy Bates from the Strategic Freight Network, Paul Weirty, who's Works Delivery, Anglia, Martin Kerno, now dearly departed and sorely missed, and Nigel Wilson, who's now also retired and is probably growing carrots. So, questions, I suppose.
Well, first off, Dave, thank you very much for your presentation. We had a few audible challenges at the beginning, but I think they ironed themselves out. I'll let people just think about any questions they may have, but what struck me, and certainly to people outside the rail industry, you know, where there's a requirement to support 10,800 homes with a new railway station, it's a simple process of just running a railway line to it and that's it. But people don't realise, you know, there's the track, the civils, the signalling, the OLE, the telecoms, you know, all the rest of it that goes with it. So if I was to ask you, excuse me, what was the biggest challenge you faced on that project? What gave you the biggest headaches?
None of it was particularly challenging. High-speed running tunnels, basically. Working out how to get those piles between the tunnels without putting a cover speed on the lines to and from Paris. That was the biggest challenge.
Right. And then going the other way, the biggest satisfaction?
Oh, the slab track and the S&C and the Unistar points. Sorry, I'm really proud of that. That's all.
Rightly so, rightly so. Well, Paul Inces made a comment about the S&C base plates and the fixings they use and the tension clamps. So that's there. I don't know if Paul's got any questions you'd like to ask whilst he's there.
No, just a good overview and good presentation from Dave. Exactly as the project went, I would say that certainly London Overground, Dave and some of his colleagues with Network Rail and the supply chain worked very hard, because I think the interdisciplinary side of things and the interfaces for a project that Network Rail initially saw as being new product, new challenging and innovation, I think there's some areas there that should be taken forward in the industry, that those due processes and design should be taken forward going on. So no, I don't have anything else specific to say. Some good detail there. Obviously, I'm now an independent consultant, but was heavily involved in the Plain Line, bridges and S&C on that project with David.
Good stuff. Thanks for that, Paul. I know Felix is on the line. Felix, did you want to add anything from your
project like this without learning something new or realising something? Sorry?
Sorry, Dave, repeat that.
Oh, yeah, you always learn something new on these projects, and that deck and that all of a sudden the light bulb went off in my head as to why we have so many problems at the end of longitudinal timber bridges, or where you've got McGregor packed slab track and it always fails for the first 3 to 4 meters inside a tunnel portal. And what we've learned at Barking Riverside actually answers why those systems. Thinking about what do we do in terms of improving how we manage rail stresses and clip stresses when you come off of a long timber bridge or you come off of pack track and go onto ballasted track. It's not all about having a really sexy ballasted transition arrangement. I think we might be focusing on the wrong things in some areas there.
Okay, thanks for that, Dave. We're getting you a bit garbled there. I don't know if you're moving around.
Oh, sorry.
We got the gist of it, I think. Felix, did you want to add any comments from your involvement with the project?
No, not from me, Colin, thanks. I think Dave covers it nicely.
Okay, well, thanks for joining anyway. If there's no other questions, I'd ask Howard just to give our vote of thanks to our speaker. Howard, are you there? I know you're there, Howard. I can see you, but we can't hear you. You there, Howard? Okay, well, look, let me do it on Howard's behalf. Dave, thank you for a very professional, insightful, technical presentation, well delivered and certainly well received. So thank you for that. I may take you up on your advice maybe in 12 months' time to have a look at some other stuff that you have involved with, because certainly your innovation that you're bringing to the table certainly warrants, getting it out to a wider audience. And like you said earlier, I think Paul mentioned, if it ain't broke, don't fix it. And if we can transfer these learnings, then why not? It all makes sense. So thank you from the Ashford section. Before closing, I'd just like to put on everyone's radar Tuesday, the 21st of March, which will be our next section meeting. We have Peter Dearman, who is the PWI president, will be presenting part of his presidential address and also a piece on electrification, because obviously the PWI isn't just about track. So if any of you are able to join us, you'll be gratefully received. In the meantime, stay safe, and I'll speak to you all very soon. Goodbye.
Thank you.